Hey, welcome back. In this video, we're going to talk more about special circuits and graphs. In the last video, we went over Eulerian circuits. And we talked about when a graph has a Eulerian circuit, and we provide an algorithm to find a Eulerian circuit when there is a Eulerian circuit in the graph. We also briefly discussed a few real-world applications of Eulerian circuits, including some applications in bioinformatics and some applications in circuit design and mail delivery. In this video, we're going to talk about a different kind of circuit. It's called a Hamiltonian circuit. We're also going to see some real-world applications of these circuits. And we're going to talk about some necessary and sufficient conditions for a graph to have a Hamiltonian circuit. We're not going to characterize the graphs that have Hamiltonian circuits in this video because this is actually a very difficult problem, and we'll talk about that a little bit. So first, let's talk about the definition of a Hamiltonian circuit. So you can recall that with the Eulerian circuit, we had to go through each edge in the graph exactly once, and we had to start and finish with the same vertex. The difference with the Hamiltonian circuit is that instead of going through each edge exactly once, we have to go through each vertex exactly once. And again, we have to start and end at the same vertex. So a circuit, when I use a circuit, I mean a closed walk, so it starts and ends at the same vertex. We can think of these Hamiltonian circuits like we thought of the Eulerian circuits as sequences. These sequences we can just think of as sequences of vertices. So a Hamiltonian circuit, we can consider it as a sequence of vertices that starts and ends at the same vertex. And there has to be an edge between every pair of consecutive vertices in the sequence. And one last requirement, the requirement that is equivalent to each vertex being visited exactly once. And that requirement is that all elements in the sequence have to be distinct except the first and last element. So if we draw a picture, we have some graph G. We have some vertices in G. And we can just draw the vertices around a circle if we want. And there might be some extra edges in the graph. That's fine. But this cycle around the outside, the first thing I drew, that circle, that would be a Hamiltonian cycle or a Hamiltonian circuit. So you can call it a Hamiltonian circuit, you can call it a Hamiltonian cycle. It means the same thing. There's also a structure called a Hamiltonian path. We talked about Eulerian paths a little bit in the last video, and we can also define Hamiltonian paths. This is like a Hamiltonian circuit, except you drop the requirement that the first and last vertex in the sequence have to be the same. So for a Hamiltonian path, you want to visit each vertex exactly once, but you don't have to start and end at the same vertex. We're going to focus on the Hamiltonian circuits in this video though, and you can define Hamiltonian graphs. And like Eulerian graphs, these are the graphs that contain Hamiltonian cycles. So a Hamiltonian graph, we can define that to just contain a Hamiltonian cycle. So a Hamiltonian graph, it's not a graph that contains a Hamiltonian path, it's a graph that contains a Hamiltonian cycle. So it's more difficult to contain a Hamiltonian cycle than a Hamiltonian path. Because obviously, if you have a Hamiltonian cycle, then of course you also have a Hamiltonian path. Just like if you have a Eulerian cycle, you must also have a Eulerian path. And similarly to with the Eulerian paths, sometimes we'll consider two different sequences as the same Hamiltonian circuit. So if two sequences pass through the vertices in the same or opposite cyclic order, they represent the same Hamiltonian cycle. For example, the cycle I drew up here, it's the same Hamiltonian cycle as this cycle, which passes through the vertices in the same cyclic order. So if these vertices were labeled 1, 2, 3, 4, and then let's call the other ones 5, 6, 7, 8. So one of our Hamiltonian cycles was 1, 2, 3, 4, 5, 6, 7, 8. And the other Hamiltonian cycle was 2, 3, 4, 5, 6, 7, 8, 1. And we could also go counterclockwise. So we could go, for example, like 3, 2, and then 8, 7, 6, 5, 4. I'm missing one. 3, 2, 1. Yeah, that fixed it. 3, 2, 1, 8, 7, 6, 5, 4. Okay, so that would be another one which represents the same Hamiltonian cycle, but we'd be writing it as a different sequence. So all of those are the same Hamiltonian cycle. And I have a problem for you to think about. So the problem is just find the number of distinct Hamiltonian cycles of Kn, the complete graph of order n. So before we go any further, I was just going to mention some examples of graphs that have Hamiltonian cycles but do not have Eulerian cycles, and vice versa. So first, a graph that has a Hamiltonian cycle but doesn't have a Eulerian cycle. So we can see Kn for n greater than or equal to 3. That definitely has a Hamiltonian cycle. On the other hand, we know that Eulerian graphs must have, if they're connected, a connected Eulerian graph must have even degree for all vertices. So we know that Kn is not Eulerian for n even. So of course, K3, the triangle, that one's Eulerian because that's an odd n. And an odd n, that means the Kn with an odd n, it's going to have even degrees for all the vertices. So that's fine. But then we have something like K4, an even n. There's not going to be a Eulerian cycle in that one. But K4 will definitely have a Hamiltonian cycle because we can just take that outer cycle right there that we drew, the C4 right there, and that gives us a Hamiltonian cycle. Now, let's consider some examples of graphs with Eulerian cycles, but not with Hamiltonian cycles. So first example, a real trivial one. Let's consider that one. So a graph with a bunch of singletons. This one, vacuously, is a Eulerian graph because since it has no edges, then there exists we can say there exists then vacuously an empty cycle that passes through all the edges. Another graph, so that one might seem a little fishy, but that one, it is vacuously considered a Eulerian graph. So any set of singletons. Here's one that maybe seems less fishy, and we saw this one before. I'll just note up here. We can even draw the one up there as a sequence of vertices and edges that starts at the same vertex. So if we label our vertices A, B, and C, we can just take the sequence A for that one. So that starts and ends at the same vertex. It includes all the edges in our graph exactly once. So if it seemed kind of fishy to call that one Eulerian, I mean, that's going straight by our sequence definition. Now this one down here, this one we also saw was Eulerian. It has a Eulerian cycle. It has multiple. So here's one of them that we drew earlier in the previous video. So not this video, but the one before. So there's one Eulerian cycle. And this one, we can see that it is not going to have a Hamiltonian cycle. And that's because this vertex right here messes things up. And we're going to talk a little more about why this one cannot have a Hamiltonian cycle in a few slides. So we'll come back to this one, but this one, I'm just providing it as an example right here as a graph that it is Eulerian, it has a Eulerian cycle, but it's not Hamiltonian. It doesn't have any Hamiltonian cycle/circuit, same thing. So we'll come back to that graph, but for now I'm going to clear this slide. I'm going to mention a few brief applications of these Hamiltonian circuits and Hamiltonian paths, actually. First application is in computer graphics, and the application specifically is to the stripification of triangle meshes. So when you're doing computer graphics, when you're processing them, you represent surfaces and volumes. They're often represented with triangle meshes. And when these are being rendered as images, the speed of the rendering engine that you use to render them will usually be bounded by the rate at which the triangulation data for these meshes can be sent to the machine. So in order to speed up that rate, it is helpful to decrease the amount of data that you send to the machine. So either compressing the data or removing certain data that is irrelevant to the rendering. And in order to do that, we can better organize the data that's sent to the machine. And that will speed up the rendering time. And in order to better organize the data, we can find a Hamiltonian cycle or a Hamiltonian path on the dual graph of the triangle mesh. And so that's a situation where finding a Hamiltonian cycle or path can help speed up the process time, rendering time for computer graphics. Another application of Hamiltonian cycles, this is the same application we saw for Eulerian cycles, and this is for CMOS circuit design. And in this case specifically, this is for multi-threshold CMOS. So again, this is a popular method for implementing power gates. And in this application, the power switches in the circuit are turned on one by one. The goal of that is just to reduce the peak current. So in order to find the best way to turn them on one by one, you look for a Hamiltonian cycle or a path in the graph representing the circuit, and you use that to determine the order to switch the power switches one by one. So these are two real-world applications of Hamiltonian cycles. I'm also going to talk a little bit about the complexity of the Hamiltonian cycle decision problem. We haven't really talked about complexity classes in this class yet. We might have briefly mentioned it in one of the in-person classes. So let me mention a few terms here. So first, this problem is a decision problem of determining whether or not a given graph contains a Hamiltonian circuit. So that question is a yes or no question. So you have some given G. Does G have a Hamiltonian circuit? So it's a yes or no. And this problem is called NP complete. So let's talk about what that means. So NP, this is a class of decision problems Decision problems, these are problems where the answer is yes or no. Now, these are special decision problems with the property that they have a polynomial time algorithm to verify affirmative answers. What does that mean? Maybe that sounds like a bunch of gibberish. Let's go into that a bit. So a polynomial time algorithm to verify affirmative answers. So what I'm saying is that when the answer to the question is yes, there exists a way to verify that answer, to verify that yes answer in polynomial time. Polynomial time in the size of the input. So size of the input graph G. So if G has order n, it's polynomial time in n. Now for this specific problem, I claim that this problem right here, this decision problem, we'll name it ham, capital H, capital A, capital M. So I claim ham is in NP. Why is that? Well, I claim that when the answer is yes, we can verify that the answer is yes in polynomial time. In order to do that, we have to provide proof of the answer, and then we have to have some way to verify that proof in polynomial time. So the proof of the answer is we provide a Hamiltonian cycle. And then we verify it is a Hamiltonian cycle. And we can do that in polynomial time in terms of n, of course. So all we have to do to verify that it's actually a Hamiltonian cycle is we check to make sure that all of the vertices in the cycle are different except for the first and last. We verify that the cycle includes all the vertices in our graph. And we verify that every two adjacent vertices in this cycle are actually connected by an edge in our graph. And of course, we can do this in polynomial time if we're given the graph. So that tells us that the decision problem ham is in NP. Now we say a problem is NP hard. We say a problem is NP hard if every problem in NP can be reduced to this problem in polynomial time. So if we can find some algorithm so that any problem in NP, we can solve that problem using this given problem, this one we're talking about, the problem ham. If we can use ham to solve any problem in NP with some polynomial time algorithm that reduces the problem in NP to ham, then that means that ham is NP hard. So this problem is ham that I'm talking about, but we can apply this to any NP hard problem. So the definition of NP hard just means that every problem in NP can be reduced to the problem with some polynomial time reduction. And ham is NP hard. So this is true. You can find a polynomial reduction from any problem in NP to ham. In order to prove that problems are NP hard, typically you take a problem in NP that's already known to be NP hard, and you reduce that problem to the problem that you're trying to prove is NP hard. So you don't have to prove that every single problem in NP reduces the problem. You just have to prove some NP hard problem in NP reduces to it. So it's not as much work as it sounds like. One more term, NP complete. This just means NP hard and in NP. So when we say that this decision problem ham is NP complete, we're saying that this decision problem is in NP and every problem in NP can be reduced to it. So it's as hard as any problem in NP, and it's in NP. So it's NP complete. That's what we mean to say that ham is NP complete. So I have some other bullets on this slide. So unfortunately, I'm gonna have to erase some stuff. But hopefully all this stuff, if it's new to you, you can rewind or come to office hours, ask me about it. Happy to discuss it. So this problem of determining whether a given graph contains a Hamiltonian circuit is NP complete. And this problem, you can be given any graph for this. And so determining whether there is a Hamiltonian circuit, it's as hard as any problem that's in NP. And it stays as hard as any problem in NP, even if you restrict it to just bipartite graphs. So even if you're only considering bipartite graphs, solving this problem is still at least as hard as any problem in NP. Even if you restrict to planar graphs of maximum degree 3, it's still as hard as any problem in NP. And of course, this problem still remains in NP even when you restrict it, because for affirmative answers, we still just provide the Hamiltonian cycle as the evidence that it is Hamiltonian. So since it's NP complete to determine whether or not a graph has a Hamiltonian cycle, clearly it's going to be difficult to characterize when graphs are Hamiltonian, because we don't even know a nice characterization for it. If we knew a nice characterization, we wouldn't have this result that it's NP complete to determine whether or not the graph has a Hamiltonian circuit, because presumably a nice characterization would give us some polynomial time algorithm to determine whether the graph satisfies the characterization or not. So in this video, we're not going to provide a characterization of Hamiltonian graphs. Instead, we're just going to talk about some necessary conditions and some sufficient conditions for a graph to have a Hamiltonian cycle. We'll start with the necessary conditions. These are slightly more obvious than some of the sufficient conditions that we'll look at. And we'll also see that graph again that I said would be making a reappearance, the H-shaped graph. So necessary conditions. So one of them I already mentioned. Every graph with the Hamiltonian cycle, it has to be connected, because the Hamiltonian cycle has to pass through all the vertices in the graph, and each step in the Hamiltonian cycle has to be between two vertices which are connected by an edge. So, of course, a Hamiltonian graph has to be connected. And we saw that Eulerian graphs don't have to be connected, because the Eulerian cycle only has to go through all the edges. It doesn't have to go through all the vertices. So there could be some singleton vertices. Now, there is a term called two-connected, which is even stronger than connected. So we say that a graph is two-connected if for every vertex in the graph G minus V is connected. And I claim if we have some graph G, so here's our graph G up here. I'll draw some vertices on G. There's our vertices. I'll even give it some extra edges. So there's some extra edges in there. Okay, and then we have our Hamiltonian cycle. We can just take that around G. And notice that if a graph has a Hamiltonian cycle and you remove some vertex from the graph, so remove this vertex, that gets rid of all of the edges adjacent to that vertex. So that edge is gone. And then I'll do a little bit of eraser here, but it's going to mess things up. So all the edges adjacent to it are gone. But as we see, when we remove the edges adjacent to this vertex, on the cycle, we're only removing two edges from the cycle. So if we're only looking at the cycle, when we remove any of the edges adjacent to this vertex, and we remove the vertex itself, we're only taking two edges off the cycle. So these two edges that were there before, they're gone now. The rest of the edges on the cycle are still there. So all the other vertices in our graph are on that cycle, and the rest of the edges on that cycle are still there. So the rest of our graph, it stays connected as long as the graph has a Hamiltonian cycle. And that's not a necessary condition for it to stay connected. This is just a necessary condition to have a Hamiltonian cycle. So we know that if it's a Hamiltonian cycle, it's going to stay connected when we remove any vertex. Because you remove a vertex from a cycle, you're not going to disconnect the cycle. So this picture I drew up here illustrates exactly what it said. And so that tells us if we have a Hamiltonian graph, in other words, a graph with a Hamiltonian cycle, this graph must be two connected. So even stronger than being connected, it has to be two connected. So if we remove any vertex, the graph that's resulting from that still has to remain connected. And that's a lot stronger than just being a connected graph. Because for example, you can consider the path Pn. And there's some vertices you remove and it stays connected. You remove this one, it stays connected. You remove this one, it stays connected. But if you remove this one, that would be bad. Then it gets disconnected. So Pn is not two connected. Cn is two connected. And the fact that graphs with Hamiltonian cycles must be two connected, this follows from the fact that Cn is two connected. So that's all we need to prove that. Also, here's another thing we get from the fact that a graph with a Hamiltonian cycle contains a cycle as a subgraph, a cycle on all the vertices. So since we have this cycle on all the vertices as a subgraph, we know that all the vertices have minimum degree at least 2 because there's a cycle that goes through all the vertices. So we look at all these vertices, this cycle, it goes through every vertex. Every vertex has at least 2 neighbors, its neighbors on the cycle. Now, we mentioned earlier, there's Hamiltonian cycles. We can also talk about Hamiltonian paths. And so if you have some Hamiltonian path, it still goes through all the vertices, but it doesn't necessarily start and end with the same vertex. There might be some extra edges here. But I just want to point out, we can ignore all those other edges and we can just focus on the subgraph, which consists of this path. So I'm going to circle that subgraph. So the one that just has the path and nothing else. So just the edges of the path. And we can see that that subgraph, the vertices on that subgraph, the interior ones have degree 2, the exterior ones have degree 1. And those are all the vertices of our graph. So we know that subgraph, when we restrict to that subgraph, the degree of the vertices on there, there's at most 2 vertices of degree 1, and all the other vertices have degree at least 2. And that tells us that when we consider the whole graph, so when we no longer restrict to the subgraph and we just consider the whole graph, the vertices in that subgraph are all the vertices in the graph. So there's no other vertices in the graph that are outside the subgraph. And we saw in the subgraph, there are at most 2 vertices of degree 1. And that tells us in the whole graph, if the graph has a Hamiltonian path, it also must have at most 2 vertices of degree 1. And all of the other vertices must have degree at least 2. I guess I'll erase that a bit so we can see the rest of that bullet, although hopefully it's kind of clear already. Okay, so those are a bunch of necessary conditions to have a Hamiltonian cycle, or a Hamiltonian path for that last bullet. Now let's discuss sufficient conditions. So there's a few well-known theorems related to sufficient conditions for Hamiltonian cycles. This theorem was proved in the middle. So these theorems were proved pretty far apart in different decades. And this one implies the next one. The next one was proved before this one. So this one, Ore's theorem, says a simple graph with at least 3 vertices has a Hamiltonian cycle if for every pair of non-adjacent vertices, the sum of their degrees is at least the order of the graph. And I claim this implies the next theorem, which is called Dirac's theorem. And Dirac's theorem says that a simple graph with at least 3 vertices has a Hamiltonian cycle if every vertex has degree at least half of the order. And so why does Ore's theorem apply Dirac's theorem? Well, if we assume that this is true, and we have some graph down here with at least 3 vertices in which every vertex has degree at least n over 2, then in this graph down here, we can consider a pair of non-adjacent vertices. So any pair of non-adjacent vertices has degree sum greater than or equal to, by definition, has to be greater than or equal to n over 2 plus n over 2, because all of the vertices in this graph down here have degree at least n over 2 plus have degree at least n over 2. So n over 2 plus n over 2, we get n. So we can see any pair of non-adjacent vertices, their degree sum is going to be at least n. So the graph down here satisfies the condition up here, and that means that it has a Hamiltonian cycle. So Dirac's theorem is an immediate consequence of Ore's theorem, and they're actually both a consequence of an even deeper theorem. And we're going to talk about that theorem, and we're going to prove it. So we're not going to prove these two. We're going to prove a generalization of them both, and they'll both be implied by the next one. And we'll talk about why they are implied by the next one. And there's something I meant to mention on the last slide, but I don't think I mentioned it. So I'm going to mention it quickly, and we'll come back to this. So on the last slide, I said I was going to come back to that graph, the figure 8 graph. So we have this graph that makes an H shape. And this graph right here, if you look at this vertex in the center and you remove it, so if that's V, G minus V is disconnected. So we saw that that graph had a Hamiltonian cycle, but I claimed in an earlier slide that that graph cannot have a Hamiltonian cycle. So it has a Eulerian cycle, but not a Hamiltonian cycle. And that's because graphs with a Hamiltonian cycle must be two connected. In other words, the graph G minus V must remain connected for every vertex in the graph. But we see for this vertex, you remove that one, it disconnects it. And so this one does not have a Hamiltonian cycle. On the other hand, all of the degrees are even, and this graph is connected. So that middle vertex has degree 4, all the other degrees are 2. So this one, of course, has a Eulerian cycle. Okay, now that was all I was going to say about that graph. Back to the other slide. So we have Ore's theorem, which implies Dirac's theorem. We talked about why that is. And they're both implied by this theorem called the Bondi Shabbat theorem. And in order to state this theorem, we need a bit more terminology. So we're going to define the closure of the graph G. It's going to be written as CL of G. And it's the graph obtained from G by adding edges UV between non-adjacent vertices UV with degree of U plus degree of V greater than or equal to the order of the graph. And we do this until there's no more pairs with this property, that the sum of their degrees is at least the order. And like I said, it's called the closure. It's written as CL of G. And the Bondi Shabbat theorem says that G has a Hamiltonian cycle if and only if the closure of G has a Hamiltonian cycle. So let's talk for a second why this implies the Ore's theorem. So Ore's theorem told us that G has a Hamiltonian cycle if degree U plus degree of V is greater than or equal to N for all non-adjacent vertices UV in B of G. And so why does the Bondi Shabbat theorem imply this? So Bondi Shabbat tells us that G has a Hamiltonian cycle if and only if the closure of G has a Hamiltonian cycle. So we can consider the graph up here. This graph, which has degree U plus degree V greater than or equal to N for all non-adjacent vertices UV in the vertex set. Now, if we know that this is true for all non-adjacent vertices UV in the vertex set, then when we find the closure of this graph up here, we're going to add edges, UV, between any non-adjacent vertices with the sum of the degrees of those vertices greater than or equal to n. On the other hand, for this graph up here, we know that that sum requirement is satisfied for all non-adjacent vertices. So when we find the closure of G is going to be a complete graph. So we're just going to add edges between any non-adjacent vertices, and all of the non-adjacent vertices satisfy degree u plus degree v greater than or equal to n. So if we add edges between all the non-adjacent vertices, then once we do that, we have edges between all of the vertices. That means we're left with a complete graph. So our closure is a complete graph of order n, because we're assuming that the degree of G is n. And like we mentioned on the earlier slide, as long as the complete graph has size at least 3, then it definitely has a Hamiltonian cycle. You just do a cycle around any ordering of the vertices. So since Kn has a Hamiltonian cycle, that tells us that this graph right here, this one, in which the sum of the degrees of any two non-adjacent vertices is at least the order, that graph must also have a Hamiltonian cycle. So we get Auré's theorem from this Bondi Shabbat theorem. So now that we see the implication, let's discuss why this theorem is true. So let's do a proof of it. So there's the Bondi Shabbat theorem, and it's an if and only if. So it says G has a Hamiltonian cycle if and only if the closure of G has a Hamiltonian cycle. So we have a forward direction, we have a backward direction. Like the other if and only if that we saw in the other video, one of the directions here is much easier than the other. So we'll start with the easier one, the forward direction. So we'll assume that G has a Hamiltonian cycle. We need to use that to prove that the closure of G has a Hamiltonian cycle. And that's pretty much immediate, because if G has a Hamiltonian cycle, closure of G has all the edges of G with possibly some extra ones, and it has the exact same vertices as G. So we can just take the Hamiltonian cycle in G, and that gives us a Hamiltonian cycle in closure of G. So that's the forward direction. That's the whole forward direction. So we have implication forward. Now we need to see why the implication goes backward. For the backward direction, we will suppose that the closure of G has a Hamiltonian cycle. Our goal here is to prove that G has a Hamiltonian cycle. Now we're going to take the closure process where we add these edges to G until we run out of non-adjacent pairs UV where the sum of their degrees is at least n. And we take that sequence and we're going to label each graph in that sequence that we get. So we started with G, and then we added an edge to G to get another graph. So we'll say G is G0, and then we add some edge to G0 to get G1, and then we add some edge to G1 to get G2, and we add some edge to G2 to get G3. And we keep on adding edges UV between non-adjacent vertices UV whose sum of degrees is at least n in the current GI to get the next GI plus 1. So again, to go from GI to GI plus 1, we just add an edge between some vertices U and V that are not adjacent in GI, but their degree sum is at least n in GI. Now, we assume that the closure of G has a Hamiltonian cycle. So that means that this GK right here, it has a Hamiltonian cycle. We want to prove that G has a Hamiltonian cycle, so we can do a proof by contradiction. We'll assume that M is the minimum possible M such that G of M has a Hamiltonian cycle. If we want to do a proof by contradiction, we want to show that G must have a Hamiltonian cycle, so we're going to assume that it doesn't to get a contradiction. So we're going to assume that G0 does not have a Hamiltonian cycle. So the minimum M such that G of M has a Hamiltonian cycle, we're going to assume it's greater than 0 in order to derive a contradiction. So there's our assumption for contradiction. We'll assume M is not 0. And we're going to say that UV is the edge that was added to G of M to make G of M plus 1. And we'll say that M is a Hamiltonian cycle in G of M plus 1. And I'm going to quickly correct a small typo here. So this G of M right here should say G of M plus 1. And we will suppose for contradiction that m does not equal -1. And that fixes everything. So let m be minimum such that g of m plus 1 has a Hamiltonian cycle. So we're trying to prove here that m equals -1, because then g of 0 would have a Hamiltonian cycle. We're going to suppose for contradiction that m does not equal -1. So if m does not equal -1, then we can say that g of m has no Hamiltonian cycle, but g of m plus 1 has a Hamiltonian cycle. So g of m has no Hamiltonian cycle, g of m plus 1 has a Hamiltonian cycle. And we'll say that uv is going to be the edge that's added to gm to make gm plus 1. And since gm plus 1 has a Hamiltonian cycle, we'll say that d is the Hamiltonian cycle in g of m plus 1. And again, we know that this edge uv exists, this edge that's added to gm to make g of m plus 1, because this is how we define the sequence here. This sequence, between every pair of consecutive graphs in the sequence, the only difference between those graphs is we added an edge to gi to get gi plus 1. So there has to be some edge uv that was added to gm to get gm plus 1. So d is a Hamiltonian cycle in gm plus 1. And we know that since gm plus 1 has a Hamiltonian cycle, so it has a Hamiltonian cycle, but gm has no Hamiltonian cycle, that means that the Hamiltonian cycle in gm plus 1 must use that edge uv. And I'm going to erase a bit. Okay. So we consider D. So I'm going to draw a picture of it. So this is D. I'll draw a bunch of vertices on it. And we know D has to have that edge UV on it because GM has no Hamiltonian cycle, but GM plus 1 does have a Hamiltonian cycle. The only difference between the graphs is this edge UV. So this edge UV is what allows us to have the Hamiltonian cycle. So UV is an edge on that cycle. We know that since it's a cycle on n vertices, it has n minus 1 other edges. We also look at U and V here, and we know by the definition of our sequence, by the definition of this UV right here, the edge UV was added to GM to make GM plus 1. And these added edges, they're edges that satisfy the requirement that the sum of the degrees of U and V in GM had to have been at least n. So degree U plus degree V is at least n, and this is, again, true in GM. And I claim that by the pigeonhole principle, there must be some edge PQ on this circuit D. So we can say like P here, Q here. So there must be some edge PQ such that both UP and VQ are edges in GM. So UP and VQ. And this is, so I claim that these two are edges in GM. And why is that true by the pigeonhole principle? So we can assume for contradiction that there was no such edge. So we can assume that for every other edge on this circuit D, we have either UP or VQ not an edge in our graph GM. And what would that mean? Well, that would mean for each of the other edges on D, at most one of P and Q is going to contribute to the degree of U and the degree of V. And so that means that when we add up the total degrees of U and V, since these are all the vertices in our graph here, so in our graph GM, when we add up the total degrees, degree U plus degree V, if each of these other edges on D, if we only have one of these two edges, UP and VQ, so we're only adding at most 1 to the degree of U or the degree of V each time we go through one of these edges, then the total sum degree U plus degree V, if this was true right here, that, so down here, if only at most 1 of UP or VQ for each BQ, then our contradiction would be the sum of the degrees, degree U plus degree V. If we only had at most 1 of those edges for each of these other edges in our circuit D, so each of these other edges PQ, if we only have 1 of these two, at most 1 of these two, so we're only adding 1 to the degree of U or V each time we go through one of the edges of the circuit. So in total, degree U plus degree V could be at most n minus 1, because there's at most n minus 1 other edges on the circuit, and we're only adding at most 1 to the degree of U and to the degree of V each time, and most 1 to the degree of either of them each time. So the total sum of the degrees would be at most n minus 1, which would be a contradiction. So that's why we can say by pigeonhole principle, there has to be an edge PQ in this circuit D such that both of these are edges in GM. And they're edges in GM because this degree sum was true in GM. What does that mean? Well, this picture, all of it is in GM except for the edge between U and V. So between U and V, that's the only part that's not in GM. So I'm going to erase that. So we have V right here. And then we have our whole cycle there. And what can we do with this? Well, we can make a Eulerian circuit. Sorry, not Eulerian. It's not Eulerian. So we can make a Hamiltonian circuit on GM, which will give us a contradiction. Because we said right here, GM has no Hamiltonian circuit, and GM plus 1 has a Hamiltonian circuit. So we'll get a contradiction with this right here. And this Hamiltonian circuit we're building, it's all on GM because I removed that edge UV. That was the edge that we added to GM to get GM plus 1. How do we make this Hamiltonian circuit? Well, here's how it goes. So we're going to start here. We're going to go to P, so U to P. Then we go around here all the way to the V. Then we go down to Q. Then we finish it up back to U. And there is our Hamiltonian circuit, and it's on GM, which contradicts the fact that GM was not supposed to have a Hamiltonian circuit. So we got our contradiction that we were looking for. And that tells us right here, our contradiction was because we assumed that M was not equal to minus 1. So we got a contradiction. That implies that since we got a contradiction, M has to equal minus 1, because our assumption that M was not minus 1 gave us a contradiction. So M equals minus 1, and that means the minimum M, such that G of M plus 1 has a Hamiltonian cycle, is minus 1. So that means that G of 0 is a Hamiltonian graph. And what is G of 0? G of 0 is G. So this G has a Hamiltonian cycle. It is a Hamiltonian graph. And that was the backward direction. So we assume that the closure of G has a Hamiltonian cycle, and we found that G itself has a Hamiltonian cycle. So I think that brings us to the end of this video. And that last bullet is just what I drew with the picture, so that it looked better as a picture, I think. Thanks for watching.